at what we call canonical form, which means trying to represent a matrix basically in some nice form. Today we are going to move to some different topic now. I will also clarify some of the doubts which come in this kind of topics. Often students are confused, especially. So this is a good point. So I will follow a slightly different method here than, let's say, like beginning undergraduate textbooks, which I believe lead to some kind of confusion. So let me begin with defining what we'll call bilinear form. So we are going to discuss first topic of bilinear form. And so our eventual aim is to understand spectral theorem for certain kind of operator, especially what we call normal operators. But why do we study that is kind of a little bit confusing in beginning, and that is why I want to begin with this topic. So we have a vector space V over a field F. Okay, and we'll fix. Of course, we have finite dimensions, so we'll say dimension of V is, let's say, n. Then a map. Let's denote this map by beta from V cross V to F. This is said to be bilinear. In short, what we call it's linear in both coordinates. But let me just write it in longhand. Said to be bilinear if beta of alpha v1 plus v2 comma w is alpha of beta of v1 comma w plus beta of v2 comma w. And similarly, in second coordinate, if I fix the first coordinate v, and if I take some alpha w1 plus w2, then again alpha comes out, and it is beta of v comma w1 plus beta of v comma w2. So the first condition means it's linear in the first coordinate, and the second condition means it's linear in the second coordinate, and that is why it is called bilinear. It's linear in both coordinates. So such maps are called bilinear maps or bilinear forms. So this is a definition. And it's quite important to understand such maps. And let's write down some example. So, very basic example. If I take some, let's say my vector space is Fn, and if I define beta of two vectors, so vectors are x1, x2, xn, and I have another vector y1, y2, yn, and I define it to be summation of xi, yi, I equal to 1 to n, then we can check that this is bilinear. Then beta is bilinear. How do we produce such more examples of bilinear forms or bilinear maps? Let us write like what you call more general example. So more general example of such a thing would be that, let's say I have again vector space Fn, and I take any matrix A in MNF, n by n matrix, and now I define beta from Fn cross Fn to F in the following way. So I define it to be beta of So let's say I denote the element of Fn as a column vector. I mean, now I have to set notation. So my elements of these are column vector, and this is column vector y1, y2, yn. I define it to be, so let's call it x, and let's call it this one y. And then I define it to be x transpose a y. So this is how I define this map beta. And it's a simple exercise to check that this is actually a bilinear map. So check that beta is bilinear. And given any matrix, I can define a bilinear map this way. Okay, but how to think of more generally a bilinear map, right? I mean, I have defined by define it in some kind of a function, but how to understand that? So how to understand bilinear maps explicitly, right? In a way, what do I mean by explicitly? Can we associate, the matrices or something like that, which we are more familiar with? So what I'm going to do is that, given any bilinear map from V cross V to F, to this bilinear map, I will associate a matrix. Let's call the matrix A. It should be an n by n matrix, and in such a way that if I want to compute this bilinear map, I can compute it in the same way as I gave this example, the previous example. So it will tell that basically that is all possible example. Okay, so that will be very nice. And how do I do that? So to associate matrix to something, what do we do? We first fix a basis. So let's say I'm given given a bilinear form. I'm given a bilinear form beta from V cross V to F, and let us fix a basis. Let V1 and so on Vn be a basis of this vector space V. All right. So once we fix a basis of a vector space, remember what we get. So if I take any vector V in V, then I can write V as a combination of this basis vector. So let's say the coordinates are going to be, so the combination will be xi vi I equal to 1 to n, and these xi's are coordinate. So this is what we do is that once we fix a basis, every vector can be written as coordinates like x1, x2, xn. So once I fix a basis, the vector space V, I can think of it as a Fn, right? These things we know already. We have done this earlier. So my claim is this. Let us define this matrix. So I define a matrix A of which ijth entry is compute beta at the vector Vi and Vj. Okay. So this is my ijth entry. You might want to call it like Aij. This is how I define the ijth entry. So I'm given beta, and I can compute all beta Vi Vj, and that gives me n square entries. I put them in a matrix like this, and my claim is that this is that A which I wanted to associate. Okay, so let's check this. Let's verify this. So let us verify this. What do I want to verify? That if I want to compute beta, I can just use A. So suppose I want to compute beta at V and W. So suppose I am given a vector V in V. So I write V as xi Vi. And suppose I am given another vector W in V. So I'll write W to be summation over, let's say, Yj Vj, j equal to 1 to n, and I equal to 1 to n. And in column form, this will become like x1 up to xn. In short, if you want to write, we'll just write it x. This in column form will become y1, y2, yn. And this in short, we'll write just as y. Okay. So what do we want to compute? We want to compute beta of v comma w, right? So let's write this as beta of v is supposed to be summation over xi vi, I equal to 1 to n, and w is supposed to be summation over yj vj, j equal to 1 to n. Now I know beta is bilinear, so it is linear in both coordinates. So let's use the linearity in the first coordinate. So I can write this as, so these xi's are scalar, they will come out. So I'll take this out, xi, and I will get here beta of vi, comma, summation over j equal to 1 to n, yj, vj, right? This is what I get. And now I will use linearity in the second coordinate here. So I can further write this. So this sum here is supposed to be I equal to 1 to n. Now I will have double sum. I will take the other sum also out. So I'll get j equal to 1 to n. Then I have xi. Yj will come out from here. So I have yj. And then what is left inside is vi, vj. And remember, this is what I wrote as an entry of that matrix. So this is what I defined to be aij, right? This is what is aij. My claim is this. Now it's just a verification that this is same as x transpose a y. Yeah. So this just requires simple verification that if you compute x transpose a y, you actually get exactly this, what I have written here. So verify this. I have done all the computations. So you need to just verify this here. Okay. So so what we did here is that to get any bilinear form, if I want to understand any bilinear form beta from V cross V to F, it can be simply obtained by some matrix in M and F. So given a bilinear form beta here, if I fix a basis, I get a matrix of size n by n. Given any matrix of size n by n, I wrote it as an example that we can define bilinear form on appropriate vector space of dimension n, right? So this is nice association of like 1 by 1. Let's write down some familiar definition. What do you call symmetric bilinear form? Symmetric bilinear form. So suppose I have a bilinear form beta, a bilinear form, form is said to be symmetric. Symmetric if it satisfies if beta of any vector v comma w is beta of wv. That means if I switch v and w, I should get the same scalar, and this should happen for all v and w in the vector space v. Right? I can make another definition of what is called skew symmetric. So let's write that down. Skew symmetric bilinear form. skew-symmetric bilinear form. So a bilinear form beta, let's write that down here. So a bilinear form beta is said to be skew-symmetric if beta of VW is minus beta of WV for all VW in V. Okay, so in skew-symmetric, if I interchange the coordinate, it should become negative of that, right? I will make another definition which is for technical reason. Maybe I'll not elaborate too much here. So when do we say something is non-degenerate bilinear form? Non-degenerate bilinear form. So non-degenerate means if I have this beta, and if I look at the associated matrix A, then determinant of A is not zero. So these are the bilinear form which are called non-degenerate bilinear form. And usually it's enough to study non-degenerate bilinear form. Otherwise, you can always reduce beta to smaller size with a zero component. So that is why we always assume non-degenerate. This also translates that if I think of beta inducing a map beta tilde from V to V star, and this map is defined as follows, that beta tilde of any vector V acting on some W is defined to be just using beta of V comma W. That means if I fix first coordinate V, there is linear in second coordinate, right? So it's a functional, it's a linear functional. So it lands inside V star. Then this map is isomorphism. So this is the meaning of non-degeneracy, that this map is isomorphism. In general, this map is always defined for any bilinear form, but it may not be isomorphism. So the isomorphism is related to it being non-degenerate. Okay. These are again, so this requires some verification, so one can do that. Okay, all right. So now what is the problem here? So let's write it down. What is the problem here? We know that whenever we change basis, when we change basis, something happens, right? So we need to understand that when we change basis, the associated matrix might change. Associated matrix may change. As we saw in the case of if you have linear transformation, and if we fix one basis, we get a matrix. But if we take another basis, we might get a different matrix for the same linear transformation, right? So the same thing happens here also, that if I begin with one bilinear form, and if I fix one basis, I get a matrix. But if I take another basis, for the same bilinear form, I can get another matrix. And as usual, you will ask the question that how they are related, right? That's the question. So let's write that down. So suppose I have matrix. I have a bilinear form beta from V cross V to F. If I fix a basis, let's say if I fix a basis, V1, V2, Vn, and we get the matrix, get associated matrix matrix A. And suppose I fix another basis. Suppose I fix another basis. Suppose we take another basis, and suppose this basis is, let's say, v1 dash, v2 dash, and so on up to vn dash, and get associated matrix, associated matrix. Let's call it A dash. So the entries of A, we can call it to be Aij here, and entries of A dash, we may call it A dash Ij if it is required. Now the question is that how A and A dash are related. How A and A dash, both of these are in MNF, and how A and A dash are related. They are coming from same bilinear form. So the question is that how they are related, right? So let's try to understand this. My claim is this. So let me write the answer straight away. Claim. There exists some matrix P such that P transpose A P is A dash. This is my claim. And this is one of the issues which I want to point it out here, especially for students in undergrad classes. Generally, we are very confused between these two different kind of equivalence relation. One equivalence relation which we defined day before yesterday, what is called similarity. So we say two matrices are similar if there exists P such that P inverse AP is A dash, right? This is not that, and this is not the same thing. This is some different relation. This is also an equivalence relation, and this is called congruence. So I'll write that down. But the two things are different. So keep this in mind. The first one originates when we are trying to write a linear transformation with respect to different matrix. This one originates when we are trying to write a bilinear form with respect to different matrices. Okay, and these two equivalence relations are different. They are not same. So let's first show this claim. So as usual, I will write V as summation over xi vi, so which gives rise to the coordinate x equal to x1, x2, xn, and similarly w, I will write it as a yj bj. This gives rise to coordinate y is y1, y2, yn. Okay, and similarly for dash, I will have a notation for dash. So I want to calculate beta of v comma w. If I calculate beta of y comma w using the basis of v, then I can write this as summation over xi vi if I'm using the first basis, and this is summation over yj vj, and we have seen earlier that this comes out to be x transpose a y. Whereas the same thing, if I use the other basis now, so this will be summation over xi dash vi dash, right? And then this will be summation over y, let's say j dash vj dash. And this time this will turn out to be x dash transpose a dash y dash. But we know that I have two different bases for the same vector space. So I can go from one coordinate system to another coordinate system, right? That is called base change. So that will give that there exists a matrix which we call base change P, such that P P x prime is x, and the same matrix will change the coordinate for the other vector also, P y prime is y. So now I will use this and substitute here. So I will look at these two here, and I am going to substitute. So you will see that if I take x transpose ay, I'll write this as P x prime transpose. I have A, and Y will be written as Py prime. And this is going to be, so by this equivalence, this is already supposed to be x dash transpose A dash Y dash. So this will become x dash transpose P transpose A P, right? And this happens for this happens for this happens for all x prime. Okay, I have forgotten here y prime. Right. So this happens for all x prime, y prime. And if there is such a equation which happens for all x prime, y prime, then you can conclude, I will leave this as an exercise, you can conclude that A prime is going to be P transpose AP. And this is what we wanted to get. So maybe it's an exercise. I should tell you what is the exercise here. Let me write here. Suppose I have something like a matrix and X transpose A Y equal to X transpose BY, and this is happening for all XY. XYs are column vectors, and A and B are matrices. Then show that A is B. This is the exercise. Okay, show that A equal to B. So we see that this is the equivalence relation we get, and now we can independently also define equivalence relation on the set of all matrices. So let's do that. So I have MNF. On MNF, we define what is called congruence relation. Congruence relation as follows. So A is congruent to B if there exists some matrix P. We want invertible matrix P invertible such that P transpose A P is B. Okay. So this is what I was saying. This relation is not same as the similarity relation. Remember, here it is P transpose A P equal to B. The similarity relation is P inverse A P equal to B. You can check that this is an equivalence relation, and this is an equivalence relation. So this is definition. Here, this is definition. Check that this is an equivalence relation. And the equivalence classes are called congruent classes. And again, the question here is, can we find nice representative? Can we find nice and simple, like we were aiming earlier? Can we find nice and simple representatives for each congruence class? Okay, this is what the question is, that can we find nice and simple representative for each congruence classes? So we'll see that we can actually indeed find some very nice representatives, and in fact we'll be able to find diagonal matrices in each one of them, and that is very important and deep theorem, and that is what one of the things comes out when you try to prove normal operator and things like that, but it gets quite confusing if you go that route. Okay, so having defined what is called bilinear form and symmetric bilinear form and skew symmetric bilinear form, and understood this question. We will answer this question, but kind of little slowly. Maybe let me write some theorems without proving them, so that you understand what I mean to say here. So let's write down this theorem, which classifies some bilinear forms. So theorem which classifying, let's say, symmetric bilinear form. Okay. So like we saw, unlike this is also a comment which I want to make. When we do very basic linear algebra, let's say in very beginning of BSc or something like that, when you study a little bit of matrices, vector space, and linear transformations, and so on, those things work over any field, right? When you're trying to solve a system of linear equations, those things work over any field. Till then, you don't realize the importance of what kind of field we should be working with, right? But as we saw when we were trying to do canonical form, the answer depends on what kind of field you have. The complication of field plays a role. For example, if you have algebraically closed field, like over complex number, then the polynomials have root. And then we had very nice theorem like Jordan canonical form. You may not have that kind of theorem if you're not working for algebraically closed field, because the minimal polynomial, characteristic polynomial may not have root, and then you cannot have eigenvalues. Like even over R, your matrices for which there is no eigenvalue, so you cannot write in that nice form. And then you need to involve some more complicated ways of writing that. Okay, so a lot of things start depending on what kind of field you are working with, and that is the same thing happens here. That classifying symmetric bilinear form highly depends on the field. In fact, let's write down some one or two important situations, and then I will tell you a little more. So first case is that let's take F an algebraically closed field. Algebraically closed field. So what happens with algebraically closed field? So the theorem says that uh, I will also, let me also assume here, just for the simplicity, I will also assume that I'm working with non-degenerate symmetric bilinear, classifying non-degenerate. As I said, that there'll be some zeros involved, so let's not worry about that. Non-degenerate symmetric bilinear form. Okay. So if I have F algebraically closed field, then there exists a basis of V such that matrix of uh, beta. So suppose this symmetric bilinear form I am fixing, calling it beta, is diagonal. In fact, I can always make it identity matrix 1 1 1 1 1. It is exactly this matrix, identity matrix. Over algebraically closed field, any non-degenerate symmetric bilinear form, I can always find a basis that it becomes a diagonal matrix. So for the symmetric bilinear form, not for any bilinear form, I'm just only saying here this theorem is for symmetric bilinear form. If I look at congruence class of symmetric bilinear form over algebraically closed field, then there is identity matrix in that equivalence class. That's what it means. However, the answer is not as nice as this if I don't take algebraically closed field. So the complication already happens when I think of real numbers. So let's take F to be real, right? We all want to know what happens with real numbers. So then what we can say is that then there exists a basis of V such that matrix of beta is diagonal, that is good, of the form of the following form. I have 1, 1, 1, but -1 can also happen. So I have -1, -1, -1. Okay. So suppose there are p many ones and there are q many -1s. Then I have n equal to p plus q. Okay. So you see that not everything is identity here. I mean, I cannot convert everything to identities. So there are now more than one uh, equivalence classes, congruence classes for symmetric bilinear form over real. Okay, so there are more than one here. For example, if you wanted to write over, let's say, for n equal to 2, I can have 1, comma 1. I can have 1, comma -1. -1, comma 1 will be kind of same, so we will not do that. -1, -1. So I can have these 3 different forms, in fact, for n equal to 2. Unlike if it was algebraically closed field, where I would have had only one of them identity. Okay. This is also called Sylvester's law of inertia. So this theorem, Sylvester's law of inertia, because this appeared first in certain situation in physics, studying some motions or something, and that is why it is called Sylvester's law of inertia. I'll make a little more comment about this maybe a little later. Can I answer over some other field? I can give another answer over maybe finite field. So if I have F is a finite field, let's say FQ, then there exists a basis of V such that matrix is, so I can always make it diagonal, in fact, in all cases, matrix of beta is diagonal of the form So everywhere I will have 1, 1, 1, but one place I'll get D. And D will have 2 choices where D can have 2 choices. I'm not telling you how to choose D right now, but I'm just trying to tell you that there are 2 possible symmetric bilinear forms here or finite field. So you see the answer is varying what kind of field you take. And it's quite challenging problem. And in fact, it's still very difficult and open problem, in fact, to understand classification, exact classification. If you say, let's say, take function field or more complicated field, it's quite difficult to understand. People who are interested in this kind of problem can look at, let's say, a book by Lamb on quadratic form. Okay, so this is reference. Later at the maybe end or today sometime, I will actually write down some references and I will put this together. So you see that problem is quite complicated for symmetric bilinear form. You can also ask the question that what happens to skew symmetric bilinear form? Can I say something about skew symmetric bilinear forms? And yes, I can give very nice answer. In fact, in that case, that case is the simplest situation. Turns out that whatever field you take, F, any field, as long as characteristic is not 2, uh, they exist. Suppose beta is non-degenerate, skew-symmetric, bilinear form. Then there exists a basis of V such that matrix of V, matrix of beta is the form 0, 1, -1, 0. So it is block 2 by 2 block of this kind, 0, 1, -1, 0, and so on. And it forces the dimension of n is even. Beta is this, and n must be even. So n must be even. Okay. This fact sometimes we can derive quite easily from knowing how a matrix of symmetric or skew-symmetric bilinear form look like. So we saw that. We saw that to a bilinear form, we can associate a matrix. Say I had bilinear form beta, then I associate it a matrix A in MNF. If beta is symmetric, the associated matrix, you can check easily, beta is symmetric, then the associated matrix here will turn out to be symmetric, which is equal to A transpose. If beta is skew-symmetric, the matrix of beta will turn out to be skew-symmetric matrix, A equal to -A transpose, right? And sometimes from here you can derive that if it is invertible, it must be of even dimension. Okay, so that is some nice answer in some example, some situation, what a bilinear form can look like. But what is the purpose of bilinear form? So bilinear forms, of course, are classified for their own interest as well. My interest, as I said, that I like group theory. My interest is in certain kind of groups. So given bilinear forms, symmetric bilinear form gives rise to a group called orthogonal group. Symmetric bilinear form gives rise to a group what is called symplectic group. So I'm going to define that for you. So let beta from V cross B to F be a bilinear form. We will always assume non-degenerate. From here onwards, we always assume beta is non-degenerate. Okay. So basically, I have a vector space V, and I have another structure on the vector space, which is this bilinear form V comma beta. Okay. It's not simply V. I have to think of the two things together. So a map, I can take an endomorphism of V. We say endomorphism of V. We say T is an isometry if beta of TV, TW, so T is a transformation, so it can apply on vectors. So TV, TW is always equal to beta of V comma W. This would happen for all V, W in V. Okay, so this is a definition. So this is a definition of an isometry. When beta is symmetric, when beta is a symmetric bilinear form, we will collect all such isometries and it gives me what is called orthogonal group. So I'll denote it by O, and I have vector space V, and I have a symmetric bilinear form OV beta. This is all those linear transformations which preserve beta. So beta of TV TW is equal to is equal to beta of V comma W, and this would happen for all V comma W in V. Okay, so take collection of all isometries, and this is called orthogonal group. This is a group, of course. Ortho. It requires to check. So I have defined OV beta as a set. So I'll give you again an exercise. Check OV beta is a group. It's a subgroup of GLV, right? So certainly OV beta is a subset of GLV. And I will define what is called symplectic. So this is one definition. I will define symplectic group. So how do I define symplectic group? So in this situation, we begin with a beta, which is non-degenerate skew symmetric. Skew symmetric bilinear form. Then I get group which I denote by SPV beta. This is again all those isometries in end V which preserve this beta. Okay, so beta of PV TW is beta of V comma W, and for all VW in V. So this is again a group called symplectic group. So this is a group called symplectic group. Now one can study these groups for their own sake. They are interesting in themselves, and they are great examples of algebraic groups, Lie groups, if you think of them, or R or C. So anybody who studies group theory certainly comes across these groups. And there is extensive literature. If you think of them or finite field, they also give example of finite simple groups. In fact, I mean, if you go modulo the center, so these groups are very, very important in group theory. But of course, we are not going to go in that direction. I want to quickly. Okay, yeah. So I think I should also tell you how to see these groups. I mean, I have written them as a linear transformation. How to think of these groups as matrices, right? I mean, I should write matrix version of this also. So, so let me write this as a matrix version, and then we take a break. So matrix version. As I said yesterday, sometimes it's good to think of these things as a matrices, but sometimes it's good to think of them as linear transformations. They have their own advantages. So let's try to represent. Suppose I have V and I have beta, and suppose fix a basis. Let's say basis is V1, V2, Vn, and then I get matrix of beta. Let's say it is A, which we know how to get it. We just defined in the beginning of this lecture. Now, suppose I have T, which is an isometry. So T from V to V, which is an isometry. So you know that isometry has to satisfy this condition. That this condition is what is called T preserves beta. So beta of any TV TW has to be beta of VW for all VW in V. So this condition will translate into matrix version, and that is what we want to write. Okay, so suppose I have vector V, and we know we can write its coordinate. So V, I can write this as a coordinate. Let's say the coordinate is x1, x2, xn, which is x, and coordinate for W is y1, y2, yn, which is simply denoted as y. Then we see that beta of VW is simply x transpose AY, right? Suppose matrix of T, so now suppose matrix of T, let's say is X with entries Xij, we want to get a condition, right? So I have to see how I can write beta of TV TW. So I have to write in the matrix form here of the first coordinate. So we know to compute TV, I have to calculate x times vector x. So it will be x times vector x is transpose. Then the matrix of beta, which is A. Then for computing TW, I have to compute x acting on y, right? This is what I get. And the condition for T to be isometry is that these two things are equal. So I get this equation that X transpose AY equal to X transpose, capital X transpose AXY. And as usual, this is happening for all XY. So I can say that the two matrices inside are same. This will imply A is actually equal to X transpose AX. Okay, so this is a very nice equation. And this is what you must have seen normally when people define orthogonal group or symplectic group directly as a matrix. So let's end with writing the definition of orthogonal and symplectic in matrix version. So to define orthogonal group, we begin with O. We have vector space V, and suppose the matrix is A. So this is my symmetric matrix. Determinant of A is not 0. Remember, which I said that is non-degenerate. Then I have orthogonal group, which is simply to say that is those elements in matrices M and F such that X transpose A X is A. Okay. And similarly, for symplectic group, I have SPVA. The dimension of V must be even, and A satisfies A equal to minus A transpose here because it is supposed to be skew symmetric. Then I have similar definition. I mean, it looks same, but the matrix A is different. So when I write the definition, it looks like I'm writing the same definition, but the matrix A is different in the second equation for symplectic group. Okay. What now? Okay. I wanted to go back to the case of the uh, real matrix case, but maybe let's take a break. If you want to ask a question, we have a couple of minutes. You can ask a question, and we will begin at 6:15. After that, do you wants to ask a question at this moment?
Sir, here you have defined the symplectic matrices uh, in your
Yes.
slide.
Yes.
This is means the order of the matrix should be even.
Order of matrix. Order of A. Yeah. The skew
Yeah,
symmetric
yeah,
matrix. Yes. Yes.
exactly. Ha ha ha.
Right. So I said that is necessary. It will, if you are assuming non-degenerate, otherwise you can always put a zero. So usually we assume that A is invertible.
Right, right, sir. If we are assuming that A is non-degenerate,
Yeah, yeah. So then it will force that A has to be of even order.
even order. Right, sir.
Right.
And for this,
So
we
that is why symplectic group always appears in even dimension.
mm-hmm. Right, sir. And sir, orthogonal matrices,
Mhm.
so those are defined on Euclidean inner product space.
Yeah, so I am doing much more general version of what you are saying. So I'm going to write that now after this, which is a very special case of what I have said so far. So
Oh,
you can
okay,
have,
sir.
yeah, you can have orthogonal group on, uh, of course, any vector space with respect to any symmetric bilinear form. And as I gave you example, that symmetric bilinear form could be many different symmetric bilinear form,
Ha
and
ha.
hence you can get many different orthogonal group. There is no one orthogonal group. So I am going to begin the next one by explaining that what we mean by usual Euclidean orthogonal group versus what I have defined here, which is much more general.
Okay, okay, sir. Okay, sir.
Yeah,
Thank you.
yeah, yeah. That's a good question. That is really confusing thing. And okay, I will clarify that little more.
Yeah, sure, sir.
Yeah. Anyone else has a question, or we take a break? Okay, so let's take a break. Uh, we'll meet at 6:15.
So we will continue in this meeting link only, right? Okay.